Hello and welcome to Lecture 3 of this unit of Phys 1101, and in this lecture we're continuing to look at friction, and we still won't even really be done with it by the end of this lecture. So just like the normal force and the tension and various other forces that we're seeing, static friction is one of these forces that always pushes just hard enough. It knows somehow how hard it needs to push. So if you are pushing on an object, as I am here, so I'm pushing on these shelves, and here's the normal due to the floor and the weight due to the earth and some force that I'm exerting on the shelves, but if they're not slipping, then we know they're not going anywhere, they're not accelerating, so the net force on them is zero. And so that tells us that there must be a force back, and it has to be the static friction. The only possible agent for this force is the floor, and that is what is preventing this object from slipping. That's why when I'm pushing on these shelves, they don't go accelerating off across the room. Well, that means for F net to be zero, that static friction force has to have a strength exactly equal to the force that I'm exerting on the shelves. And if I push harder and the shelves still don't slide, then that static friction force must have increased to exactly cancel the force that I'm exerting on them. So here is a simulation for learning from a great organization called PhET, Physics Education Technology, and I'll put a link to PhET below the video on YouTube. And here we have a box which I've put on this ramp, and there's a little person over here, and I can make them push the box, and I'm going to bring up a free body diagram, and I can either make the person push by clicking and dragging on the box, or by clicking and dragging on the free body diagram. And now, just to simplify things a little, I'm going to lower the ramp down to a 0-degree angle, and then I'm going to push and watch. The frictional force is increasing to directly compensate. But there, the box started to slide. So watch that again. I'm going to push, push, push. Friction force is increasing, 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 and bang. Oh, look, the friction force decreased in its strength at the moment that the box started to slide. And that's because at that instant, the static friction force, which I've set to have a coefficient of 0.5, got replaced by the kinetic friction, which has a coefficient of 0.3. And if you look on the tables, you'll see that kinetic friction coefficients are always lower than static friction coefficients. Let's see how this plays out again for a box on a slope. So this is a lot like in the last lecture, but I've reduced the angle, and I've said now the box is stationary. Now, really, we should check whether the box even can sit here without sliding down the slope, but we don't know how to do that yet. We'll know that in a bit. So let's go ahead and proceed as if we knew that it isn't going to slide down the slope. So things are going to play out a lot like before. The only thing the box is in contact with is the ramp, and so there's going to be a normal force, and the static friction has to prevent the box from going down the slope, right? If there were no static friction, the box would accelerate down the slope, and so the static friction must point up the slope. And so there is our free body diagram, looking much as it did before. But the big difference now is that this box is not accelerating, and so F net is 0. And again, it's going to be more convenient to work with tipped axes, because we have two vectors which are tipped and one that isn't. We should break up our weight the way we did before, and it plays out just like it did before. And so I'm going to skip over that quickly and go straight to writing Newton's second law. And this, again, will go much as it did before, except that this is now static friction. And, oops. And this is now 0. F net is 0. And the y component looks exactly like it did before. And again, it's a good idea to count your unknowns. We don't know the normal or the static friction, but we do know all of this, including sine and cos of 20 degrees. Those are just numbers. Your calculator can tell you what they are. And so, we only have two unknowns, which means we can go straight ahead and solve, and the only thing we want is fs. And it's all by itself as the only unknown, and so it's just mg sine 20 degrees. And you could punch that into your calculator now and get it as a number, but as far as I'm concerned, we're done. So now that we've seen how we solve for a static friction out of Newton's second law, just like we do for normal forces and so on, and so the static friction pushes just hard enough as long as the thing doesn't slip, it pushes just hard enough until it can't push any harder. You know that if I push hard enough, I can make those shelves move. And so at that point, what will have happened is that I will have exceeded the maximum strength that the static friction can have. And it has this form, very similar to what we saw for kinetic friction, but you have to be careful. This works differently from kinetic friction, because notice, this is not a formula for the value of the static friction. We've already seen we have to solve for it in general out of Newton's second law. But this tells you what the maximum force exertable by the static friction is. So this is a really common error that students make, where they just assume they can calculate a static friction using μs times n. You can't. All you can do is use this to set what the upper limit is on the static friction. So now that we know how to find maximum static friction forces, we can answer a different question about what the maximum angle is of the ramp before the box slips. Because you probably know intuitively, if you just take this ramp and tip it up higher and higher, eventually this box will start to slip. Well, we can figure out what angle that is, and this has lots of application in engineering and geology, angle of repose of a slope, and so on. So I'm going to just change a few things. This is basically our solution from before, but I'm going to say, okay, now instead of 20 degrees, we're working with some unknown angle. So I'll call it theta, and I'll put it down in here, and nothing has changed. Our Newton's second law is exactly what it was before. And you may be saying, oh, but hang on. Aren't we looking for when it starts accelerating down the slope, and so F net shouldn't be 0 anymore? However, this is a little subtle. We're looking at the maximum angle such that it doesn't slip. So we're going to assume it doesn't slip and find what maximum value of theta makes that true. So our free body diagram is exactly like before. Our F net is still 0, and so our Newton's second law gets written out exactly the same way, except with this unknown angle. And if we again count unknowns, the normal and Fs are unknown, but also because theta is unknown, now we have a third unknown again, and it's actually a little nasty, because that unknown is inside sine and cos functions. Well, it turns out we'll be able to deal with that. So again, we don't have enough equations. However, we can fix that because we are looking for the maximum angle, and that means we are looking for the maximum value of static friction. This is often called being on the verge of slipping. You'll see that in a lot of textbooks. So we're on the verge of slipping here. If we make the angle any larger, this box will start slipping. And on the verge of slipping, now Fs is its max value, which is μsn. And so we're wood on wood again, so we know μs. And so we haven't added any new unknowns now. We have 3 equations and 3 unknowns, and we can solve. So I will take my fx and I will solve it. I'm going to say now mg sine theta, I'd like to solve for theta, is fs, which is mu Sn. And again, I can't solve that yet because n is unknown, but as before, n is just mg cos theta out of the y components. And so now I have mg sine theta is mu s mg cos theta. And a little bit of magic occurs. Look, mg is on both sides. Mg can divide both sides by mg, and that's all gone. And so finally solving that, I get that mu s is sine theta divided by cos theta. You may or may not know that's tan of theta. That's a handy thing to know, which means I can now solve for theta by taking the inverse tan. And if you plug that into your calculator with the mu s of 0.5 for wood on wood, you're going to find that that gives you something around 27 degrees. Now really, before, when I had set this angle to 20 degrees, we should have checked whether that exceeded this before deciding that we were able to calculate Fs. But we see now that we were okay. So let's talk a little bit about the mechanism of friction. And I don't mean a machine. When a scientist says mechanism, they mean a way of describing something in terms of something simpler. Friction is complicated, so it would be nice to understand it in terms of simpler ideas. And indeed, it turns out that kinetic and static friction are caused by normal forces, but at the microscopic level. So because of surface roughness, those normal forces can point in all sorts of different directions. Now, you've probably heard that on the microscopic, or at least on the atomic level, surfaces don't actually touch because atoms repel each other electrically. But we want to think on a slightly larger scale than that. And even on that scale, surfaces only touch each other at a few places. And now if you push, these angled normal forces will oppose that push. If you push hard enough, eventually the bumps on one surface will ride up out of the troughs in the other surface, and they'll start skipping along over each other. Chemical bonding also plays a role. Wherever the surfaces do touch, molecular bonds will form, and one of the reasons static friction tends to be larger, or can be larger than kinetic friction, is that these molecular bonds form, and then you have to break them before the two surfaces will move. So friction still has a lot of tricks up its sleeves, and we will keep running into it as we go on. Before we move on a little bit from it, we've been ignoring rolling friction up to this point, and I'll just explain why. We'll continue to ignore it most of the time, because if you look at these rolling friction coefficients, they're very small. So rolling friction has a tendency to be quite a small force. Its mechanism is a little different from the other frictions. It's still due to breaking of molecular bonds, but it's also due to compression of the surfaces, and that actually tells you there's something else going on here. If you think of your car tires, if they are underinflated, they compress more, and so in fact this coefficient of rolling friction can be dependent on how inflated your tires are, and this is why you get poor fuel efficiency if you underinflate your car tires. Friction doesn't depend on the speed that the surfaces are moving across each other, and it also doesn't depend on the surface area in contact, except that all of this, the equations, this idea of being independent of speed and surface area, this is all just a rough model. And in fact, we don't even really know when this model works and when it fails to work. So this is an area of active research. This is really one of the frontiers of physics.